A gyroscope measures the rate of rotation around an axis. In an aircraft, a gyroscope is used as a turn coordinator or heading indicator. It is used exclusively for navigation on unmanned aircraft and in compasses. It is used in boat stabilizer systems to keep a boat with a high center of gravity from tipping over. You probably know it best from the app in your phone, from playing video games, or for its use as an image stabilizer in digital photography. The first mechanical gyroscope was invented in the early 19th century. It was combined with electric motors late in the 19th century to provide navigation devices for the world's navies. The gimbal allows the rotor to keep spinning without applying further torque. Due to conservation of momentum, it resists any force that attempts to change its orientation. The rotor maintains a constant angular orientation as long as no torque is applied to the gyroscope. Unless you've worked hands-on with gyroscopes, it isn't that easy to visualize how it moves in 3D space. I found some excellent videos online that visualize the motion for you. Please check these video references and watch. It is well worth your time. A gyroscope in an aircraft is mounted inside a bearing in a special vibration-proof housing at a fixed angle parallel to the Earth's surface. The housing and position sensors rotate with the aircraft, but the gyroscope does not. Of course, each rotational axis of the gyroscope needs to be powered by an electric motor. At zero attitude angle, the position sensors measure nominal angular position. Shown in this slide is a 45-degree angle between the horizontal rotor and an electrical contact. When the aircraft engages in a roll maneuver, shown in the bottom diagram, the contacts rotate relative to the gyroscope. In this diagram, the angle between the horizontal rotor and the contact is now 35 degrees. This means that the aircraft is oriented at a 10-degree roll angle. A mechanical gyroscope can also be used to measure angular velocity in an aircraft. An aircraft rotates around one of its three orientation axes: roll, pitch, and yaw, as shown in the diagram. Each of these axes has its own gyroscope to measure angular velocity. The input axis of the gyroscope corresponds to either roll, pitch, or yaw. The gyroscope rotates when the aircraft rotates around the input axis. The net torque applied to the gyroscope causes precession to occur. Precession is the change in the orientation of the rotational axis of a rotating body. The angular momentum vector rotates in the direction of the torque, which means in this case that the spin axis rotates about the output axis. The gyroscope senses the angle of rotation. It feeds a signal to a motor to rotate the input axis in the opposite direction to the aircraft rotation, until the spin axis moves back to its original orientation. The motor temporarily negates the precession, at least until the aircraft rotates again. The amount of rotation is divided by the amount of time to rotate in order to calculate the angular velocity of the gyroscope. This, of course, equals the angular velocity of the plane. Each of steps 3 to 7 in this recipe is repeated as long as the aircraft is still rotating. If the number of calculations is large enough, you can also take the differential of the velocity over time in software and calculate an angular acceleration. A MEMS vibratory gyroscope measures angular velocity via the Coriolis effect. Remember that one? It was the core principle used in the Coriolis flow sensor. The basic concept of this gyroscope is shown in the diagram on the right. A proof mass is suspended by a supporting structure, with the comb fingers acting as both spring and damper elements. The proof mass is free to oscillate in the X and Y direction. It is vibrated along the Y-axis by the electrostatic drive input. In response to rotation of the sensor about the Z-axis, a Coriolis force causes the proof mass to also vibrate along the X-axis. The vibration along the X-axis is sensed by the change in the capacitance of parallel plates positioned along that axis. Let's study how the Coriolis force creates the vibration along the x-axis. Recall that the Coriolis force is equal to the cross product of motion along two mutually perpendicular axes. In our case, the sensor is vibrated along the y-axis. The sensor is attached to an object that is rotating around the z-axis. The magnitude of the Coriolis acceleration is minus 2 omega v, where v is the linear velocity in the y direction and omega is the angular velocity of the structure around the z-axis. The Coriolis force is the proof mass times the acceleration, which is minus 2m omega v. Let's look at a spec sheet of a 3-axis MEMS capacitive gyroscope. This device is a low-power 3-axis angular rate sensor. It includes a sensing element and an IC interface capable of conveying the measured angular rate to the application through either a SPI or I2C interface. You can select the full-scale output, either plus or minus 245, plus or minus 500, or plus or minus 2000 degrees per second. The zero rate level describes the actual output signal if there is no angular rate present. Recall that we had the zero stability signal in the Coriolis mass flow rate sensor. The zero rate level in this MEMS sensor results from internal mechanical stress in the sensor. It can change after the sensor is soldered to a PC board, but little over time and temperature after that. The sensitivity is given in millivolts per degree per second. The nonlinearity is erratic, with a nominal of 0.2% of full scale, but with worst case being plus or minus 5% of full scale. These devices are difficult to calibrate and maintain consistently during manufacturing. The block diagram for the drive circuitry should look familiar to you by now. We need a charge amplifier to convert the charge on the 3 capacitance circuits, one each for rotation about the x, y, and z axes, into voltages. Because the signals are sinusoidal, we feed them into a low-pass filter and then an ADC to get an angular velocity readout. The signal requires some post-digital filtering so that the output to the I2C or SPI interface is stable. This wraps up our module on position and acceleration sensors. We will study motion, distance, and humidity sensors in the next module.